Welcome to this lecture. This lecture is the study of quantum mechanical harmonic oscillators. So let us have a brief review that what I am going to talk about in this lecture. I divided this lecture into small parts. So we'll just talk about harmonic oscillators first of all. That how I divided my lecture. So as harmonic oscillator is a classical problem. We studied this at +2 level, where we solve a simple differential equation. Then we study this in BSc level, and then after that we will study this problem in classical mechanics at PG level, where we will make use of Hamiltonian approach to solve this equation. So there are different ways to solve this problem of harmonic oscillators. So one is the classical treatment, and another is the quantum treatment. And quantum mechanically, we will try to solve this problem by using two different methods. One is the analytic method. Here we will make use of wave mechanics. And another approach is the matrix algebra approach. So we will study these two approaches at +2 level, at UG level, and we studied this at UG level in quantum mechanics course. And here at PG level, we will try to solve this problem of quantum harmonic oscillator using matrix algebra approach. Right. So I will briefly talk about classical treatment of the harmonic oscillator, then analytic method of the harmonic oscillator in this lecture, and then in the next lecture I will talk about matrix algebra approach to study the quantum harmonic oscillator problem. Right. So let us do these two parts in this lecture. I basically briefly review these two. I'm not going to talk about these in very detail. So this is a classical harmonic oscillator. So say it is a mass m, it is attached to a spring whose spring constant is k. Then the system is set to execute a simple harmonic motion. If this is displaced to here by applying certain force, then this restoring force acting on it is minus kx, then we can say that this is simple harmonic motion. But force is nothing but force is mass into acceleration, or I can say that d square x by dt square. So therefore, if I club these two equations together, then what I am getting, md square x by dt square is equal to minus kx, or I can say that d square x by dt square is equal to minus k by mx. Here let k by m is equal to omega square. If I use this, then this equation will become d square x over dt square minus omega square x. So that means this will become a standard differential equation, and we can find out the solution of this differential equation easily. And the solution of such an equation looks like this, that x must be equal to, there are another possible solutions, but I am considering a very simple solution. So it is a sine omega t plus b cos of omega t. So this is the solution of this equation, and we can calculate the kinetic energy, and kinetic energy comes out to be half mx dot square. So from using this equation we can calculate x dot, and potential energy of the system is given as half kx square. This is the potential energy, and total energy can be calculated as half ka square. A is basically the amplitude, this amplitude of the wave. So let us try to represent these results mathematically. So if I try to plot the wave function, it must be like this, right? It is time axis, say it is x-axis. So if it executes simple harmonic motion, then wave function changes with, or this x will changes with time in this manner. And let us have a look at the energy plots. So what happens to energy? So say it is the x, and say it is the kinetic energy, sorry, it is the total energy of the system. It is the total energy, and say half kx square is the potential energy of the system. It is the potential energy, and similarly we can have a look at kinetic energy, and the plot of the kinetic energy looks like this. It's a inverse parabola, right? They are parabolic in nature. So this is the total energy, and it is nothing but is equal to half ka square, and here this is the potential energy and this is the kinetic energy, and here is the x, it is the origin, right? And this is y in the y-axis, and this along y-axis there is energy. So this is the graphical representation, and all of you are familiar with this result. Now next I will talk about quantum harmonic oscillator. Next is the harmonic oscillator, and here I am going to talk about its analytic method. I am briefly reviewing it. I am not going into the detail of this method. I am just writing the Schrodinger wave equation and then write down the final expression. Right. So for this, let us proceed as follows, because we have to express the kinetic and the potential energy, because it's a quantum treatment. So that means this kinetic energy and potential energy both should be written in the form of operators. So let us talk about that first of all. As we know that potential energy is equal to half kx square, where k over m is equal to omega square, so k is equal to m omega square. So this will become half m omega square x square. But if this is the operator of position, then potential energy can be written in the form of operator m omega square this, right? And kinetic energy can be written in the operator form. It is p square upon 2m, where this is the momentum operator, right? So that means, using all these things, Hamiltonian for the system, Hamiltonian for this Hamiltonian can be written as, this Hamiltonian operator is equal to kinetic energy of the system plus potential energy of the system, right? And the corresponding Schrodinger wave equation can be written as, this h psi is equal to E psi, where E is the eigenvalue of the energy, is known as eigenvalue of the energy. So if I substitute the values of these operators, then how I can write down p square by 2m plus half m omega square x square, it's psi, is equal to E psi. Here P is the momentum operator, and it is minus iota h cross d over dx. So therefore P square, it must be written as minus h cross square d square over dx square. And let me write down it as equation number 2, and let me call it as equation number 3. So if I substitute these values in this equation, and also I know that x operator is simply equal to x. So using equation number 4 and 3, what I am getting, minus h cross square by 2m d square over dx square plus half m omega square x square. This psi is equal to E psi. Now multiplying with this reciprocal of this on both sides means multiplying both sides with minus 2m over h cross square, because I want to eliminate this from here. Using that, I can write down this equation as this is d square psi over, and multiplied this psi with here and here. So d square psi over dx square plus minus m square omega square over h cross square, and it is x square, and psi must be equal to minus 2me over h cross square into psi, and this equation will become d square psi over dx square plus 2me, bringing this towards this side, over h cross square minus x square over x naught 4. That means I have chosen this value as this whole of the quantity as x naught raised to power 4. We'll talk about it after writing down this equation. So that means what I did, I've chosen that 1 over x naught raised to power 4 m square omega square over h cross square. So that means 1 over x naught square is equal to m omega over h cross, or 1 over x naught is equal to m omega over h cross under the root, or I can write down x naught as h cross over m omega under the root, right? Why I'm writing it as x? Because if I try to look at it, then its dimensions are equal to length, means having dimensions of length. That's why I'm choosing it as x naught. So this is about differential equation. It's a very important differential equation for harmonic oscillator. Now our purpose is to solve this differential equation, and the solution of this differential equation is a little bit tricky, and for that we have to make use of the Hermite polynomial. That is a very rigorous mathematics, but I am not going into detail of that mathematics here. So I am directly writing the results. So eigenvalue energy corresponding to this equation now eigenvalue of energy of this equation is given as that En is equal to n plus half h cross omega. That means energy of the oscillator is a discrete and equally spaced. Only equally spaced means discrete values of energy as possible, and wave function can be written as that this psi nx is equal to 1 over root pi and whole under the root 2 raised to power n factorial into x naught e raised to power minus x square over 2x naught square into h n x over x naught, right? So here let x over x naught is equal to y, then I can write down it as, here that means h and y is known as Hermite polynomial of order n, or nth order polynomial, and known as Hermite polynomial, and its value is given as Hermite polynomial can be written in the form of a recurrence relation. So using this recurrence relation, one can calculate this h naught y is equal to 1, h1y as equal to 2y, h2y is equal to 4y square minus 2, and h3y we can calculate 8y cube minus 12y, and if I use this, then we can write down the corresponding wave function also. So the wave function psi naught can be written as 1 over root pi x naught exponential of minus x square over 2x naught, right? And similarly we can calculate the value of psi 1, and the value of psi 1 will be 2 over root pi x naught cube whole under the root exponential, sorry, x is also there, exponential minus x square over 2 x naught. Then I can also calculate psi 2, and the value of psi 2 will be 1 over 2 root pi x naught whole under the root into 2x square over x naught square minus 1 exponential minus x square over 2x naught square. And this psi 3 can be written as 1 over 3 root pi x naught whole under the root 2x cube, it is 2x cube over x naught cube over x naught cube minus 3x over x naught into exponential of minus x square over 2x naught square. So this is a way that how we can write down various wave functions. Now let us try to look at all these mathematically. So let us have a look at graphically. So let us look at the graphical representation. So it's a so this is parabolic potential. It's like half kx square, right? So in this potential particle is confined. So if I try to look at, so ground state energy is corresponding to n is equal to 0. So corresponding to n is equal to 0, there is energy half h cross omega. Then corresponding to n is equal to 1, the energy will comes out to be 1 plus 1 by 2 h cross omega. So it is 3 by 2 h cross omega. And corresponding to n is equal to 2, it will be 2 plus 1 by 2 h cross omega. So it is 5 by 2 h cross omega. Right, so these are the discrete values of energies which are possible for quantum harmonic oscillator. And if we try to plot the wave function, then we are having a very different type of wave functions. So let us try to look at those wave functions. So it is x, it's 0, it's equilibrium position. So at equilibrium position, the wave function looks like this. Right, this psi naught, it is a plot of this, and the plot of another wave function is like this, psi 1. So that means, and corresponding to next wave function, it's a wave function called. So it is the wave function of psi naught. This is the plot of psi 1, and this is the plot of psi 2. Here the probability will be maximum at the origin, and here the probability in these regions will be maximum, and here these are the 3 regions. So for probability, otherwise we will talk in terms of this what we call their amplitude, square of the wave function. So if I try to look at the square of the wave function, then that can be plotted in this manner. So corresponding to this wave function, say it is x So it is the 0 for all the graphs, so its graph will be like this, right? So it is psi naught square. So and corresponding to it, the wave function will be like this. So it is basically psi 1 square, and corresponding to it, the wave function should be like this. So it is psi 2 square and so on. So here we will talk about different probabilities in the different regions for different states, means the ground state, first excited state and second excited states, and so on. So that's all for this lecture, and now in the next lecture I will talk about the mathematical formulation or for the harmonic oscillator using matrix algebra. So thanks for watching this lecture.